Hello guys, I am Tarun from Chemical Department from IIT Madras. Now let us discuss the second module of course ME 1100. So in this module, first we will discuss about pure substance. So now let us discuss about initially let us discuss about Gibbs phase rule. So here we know the formula of Gibbs phase rule where F is degrees of freedom that we can write C plus 2 minus P where F we can say minimum number of independent properties so that are required to explain a system, or we can say to explain a system, or we can say where in that area is to explain that area where we are interested. So and here also C is the number of components, and P is P is number of phases in thermodynamic equilibrium. So now let's discuss change of phase. So here change of phase hitting at P equals to constant. So this is PV graph where phases are changing, and we are hitting the system at constant pressure, and we are observing how phase are changing. So here this is solid liquid, this is solid liquid, this is solid liquid equilibrium line, and this is solid plus liquid region. Here this is critical point, here this is solid plus vapor, and we can say this is triple line. Now now this is change of phase, this is also changes of phase. Here P and T both are increases. This is PV diagram. This is for water whose volume decreases after melting, and this is for substance whose volume increases after melting. So this is a bit different from previous. Now critical point and triple points. So critical point, we can say critical point specifies the conditions temperature pressure above which distinct liquid and vapor phase keys were to exist. And triple point, we can say triple point of a substance is the temperature and pressure at which three phases gas, liquid and solid of that substance may coexist in thermodynamic equilibrium. So now change of phase heating at pressure equals to constant, and this is TUV diagram. So this region is subcooled compressed liquid. Here this path and this path. So in when we go path from here to here, then P increases. This is superheated vapor region. This is liquid plus vapor region. Now we can denote some points like F, G, F star, G star, where the phases are changing. Where the phase is changing. So this is change of phase PT curve. So this region is solid phase critical pressure. This is triple point. This is critical point, and this region is supercritical fluid. This region is for compressible liquid. This region is for liquid phase. This region is for vapor. This region is for gaseous phase, and this region for and this is critical temperature and critical pressure. This is triple temperature, and this is triple point pressure. Now, yeah, we are here. So next change of phase, we will discuss about quality or dryness fraction. So this is PV curve where this is also same like previous. Here this is critical point, This is these are some points. Air pressure increases. This is superheated vapor region. This is saturated vapor region. This is liquid plus vapor region. Now, now we can denote dryness fraction by x equals to mg, mass of gas, mass of gas divided by mass of liquid plus mass of gas. So this is the mass fraction of gas. So where xf is 0 and xg equals to 0, here xf 0 and here xg equals to 1. So we can denote molar volume Vi like Xi into Vg plus 1 minus Xi into Vf, and molar internal uh, energy, and we can denote also enthalpy like this. Now let's discuss first law for control volume. So for control volume, so this is the layout of control volume. Here this is inlet stream and this is outlet stream. So control volume is defined as the fixed volume on which our attention is focused. Apart from the energy interaction, is it also allows inflow or outflow of mass. So through entry and exit ports respectively. So now derivation of first law for CV. So let us consider single inlet and single outlet situation. So when, let's say at time t, let's say at time t, so at t time t, this is mcv at time t is mass of control volume at time t. This is dmi, where dmi mass entering from inlet stream and at time t, and some energy del q is also entering from inlet stream. Now at time t plus delta t, after that time delta t, so after delta t time we can say mcv t plus delta t. This is mass of control volume at time t plus delta t, and this is dme, mass living through outlet stream, and this is delta w, some work is done. So now mass conservation for CV. So at time t, so fluid mass we can write like this dm, so mcv plus dmi, and fluid mass occupied by control volume also we can write mcv at time t. So at time t plus delta t, fluid mass we can write mcv t plus delta t plus dme. Dme is living mass. So fluid mass occupied by control volume we can write mcv t plus delta t, mcv at t plus delta t at time t plus delta t. So mass conservation. Further, we can write total mass at time t, that is equals to total mass at time t plus delta t. So d by dt of mcv we can write dmi by dt minus dme by dt. So mi dot minus me dot. Mi dot rate of change of mass and rate of change of entering mass, and me dot rate of change of leaving mass. So for steady state, no time dependence. So rate of change of entering mass and rate of change of leaving mass will be same at steady state. So now energy conservation. So total energy of the system at time t, we can write ECV at time t plus DMI into UI plus VI square by 2 into GZI. And also we can write like this at time t plus dt. So the net flow work done over a time interval delta t. Further we can write like this minus DMI rho 1 V1 minus dmi p1 v1 plus dme pve. So by first law we can write del q minus del w external plus dmi like this minus dmi like this. So that is equal to ecv at time t plus delta t minus ecv at time t. So for multi inlet and multi exit ports, we can write DECV by dt. Change in total energy of control volume, we can write Q dash minus W dash external plus summation of total inlet stream. Summation is for total inlet stream. So if we say there are four inlet stream, so there are three inlet stream. So summation we are writing to ends all inlet streams. So summation m dot I hi, like this these terms. So if we write for single exit and inlet ports, so where we will write only m dot I and only m dot e. Now for steady state, so for steady state we know uh, d by dt equals to 0. So and for steady state also dmcv by dt equals to 0. So therefore the steady state, so at steady state energy equation, uh, we can write like this: q dash minus w dash external equals to m dot into h plus ve square by 2 plus में ggid minus m dot into this term. So let us discuss about flow nozzles and diffusers. So so for flow nozzles and diffusers, how can we apply energy equation or energy balance equation? So in flow nozzles and diffusers, we will consider no heat and work interaction, no heat and no work interaction between system and surrounding. And at flow and at nozzle and at diffuser, we can also include change in potential energy negligible, but we cannot include change in kinetic energy as negligible. So many times in nozzles, inlet velocity may less than outlet velocity, and in diffusers, mostly time. So inlet velocity uh, is greater than outlet velocity. So now conservation of mass. So we can write conservation of mass equals to m dot equals to rho I ai into vi equals to rho e ae into ve. So this is change of mass. This is sorry. This is rate of mass entering, and this is rate of mass leaving. So those are equal. So these are equal, and applying steady flow energy equation. For nozzles and diffusers, we can write like this: Q dash minus W dash external equals to m dot into H plus VE square, like this. And here ZD is 0 and ZI is also 0. So we can say these two terms are equal. So here we can say these two terms. We can say this term is H naught E, this term is H naught I. So these are equal. Okay, so that was our second module. Okay, thank you.